Extraction of road network from satellite images using efficient net, a deep learning approach. Abstract satellite images are great examples of high-resolution images that represent a wide array of information about the surface of the Earth. Analyzing such high-dimensional images and gaining insights from them is a crucial task, and this analysis can provide solution to various kinds of problems. But analyzing and gaining insights from such high-resolution images is a difficult task and requires a lot of computation. The problem that we have considered for this study is identification and extraction of the road networks from the given satellite images using neural network. As observed in the past, the main aim of a supervised learning research is usually higher accuracy and not efficiency. But in this paper, we try to find a solution to this problem that is not only has high accurate but also is efficient in terms of time and space complexity. The reason for this study is to come up with solutions that can be deployed on low compute devices such as edge devices, especially during inference time. This problem comes under pixel-wise semantic segmentation, and we have done a comparative study on few models that are able to provide potential solutions for the problem. Keywords: road network, semantic segmentation, convolution, ResNet 18, efficient net, benchmarking. Introduction. Satellite images are able to capture high-resolution images of the surface of the Earth, which creates a diverse set of data which can be useful for various kinds of analysis. High-resolution satellite data can be made available for any particular remote region on Earth. It can be used in a wide array of useful applications ranging from military surveillance, architecture and building purpose, agricultural purpose and disaster management. The type of analysis to be performed on these satellite images depends on the application. One great example which we will be focusing on in this paper is road network extraction. Identification of road networks from satellite images is a problem wherein the satellite images are broken down in clear visualization of important information which we need at the moment. Identification of road networks from satellite images is a difficult task, and one way to approach this problem is for a human to manually identify and annotate the image, but this is a tedious task and not feasible in a long run. A better way is to make someone annotate a few images and train a machine to learn from that data and make appropriate predictions. Initially, we explain our details of our dataset, such as the types of images, their dimensions, and the task to be performed using this dataset. Though we review some of the existing methodologies for our problem. Then we propose a potential architecture and try out different variants of those architectures and record the results. Then in the end, we derive the conclusions from the observations of our experiment. 2. Dataset. The dataset that we used is taken from Deep Globe 1.2 Road Network Extraction Challenge. It contains 4,484 images for training, 50% of which include satellite images and the rest are their corresponding output masks. Each image has the resolution of 1024 x 1024 pixels and has 3 color channels, i.e. the image is in RGB color format. Each pixel of the image represents 50 cm per pixel of ground resolution. These satellite images as seen in Fig 1 are captured over Indonesia, Thailand, and India. These images are sampled, labeled, and segmented by GIS experts. Out of the total 4,484 images, we took 4,000 images for training and the remaining 484 images were used for validation, which is roughly 10% of the training data, and a lot of images are provided as test set whose ground truth is not available. 3. Literature survey. In this literature survey, we review few of the top performing architectures in the Deep Globe Challenge. Although these architectures were trained on 4,484 images as training data and validated on separate 1,243 images, the ground truth of the validation set was not available for our research, so we made use of the training set and sampled a validation set from the 4,484 images. The results produced by our research are different from the results achieved in the challenge, and so we have produced our own baseline as a comparison metric. Fig 1. Road network annotated from satellite images. In this paper 3, the authors have suggested that from a satellite picture, it is troublesome and computationally costly to extract streets because of quality of other road like highlights with straight edges. They have suggested a methodology for automatic rote extraction which will be based on a fully CNN of the UNet family. This network comprises of ResNet34 pre-trained on ImageNet and decoder adjusted from vanilla UNet. The best open score of their model on the Open Leaderboard is 0.64. In this paper 4, stacked UNets are utilized with various outputs for street network which needs to be extracted. The problem of uneven classes of training data is solved using a hybrid loss function. Post-processing techniques which include street map vectorization and shortest path search with progressive thresholds which basically helps in improving recall. The overall improvement of mean IOU which when compared to the vanilla VGG network is more than 20%. In this paper 5, the authors proposed a LinkNet architecture that makes use of dilated convolution as its main component. This was the winning solution of the challenge and had invalidation and test IOUR 0.6466 and 0.6342 respectively. For proposed system. As seen in the Fig 2, there are two aspects to be considered while selection of architecture for semantic segmentation. Model: this is essentially the main scaffolding of our architecture. The models used for our problem are UNet 6, LinkNet 7 and Feature Pyramid Network, FPN, 8. Backbone: this can be thought of the actual building blocks of our architecture. This actually tells the number of layers, convolutions, pooling etc. and their flow. For our study, we have used two backbones, ResNet 18.9 and EfficientNet B010. A algorithm. The table 1 below is a generic format for our algorithm and all our architectures follow this algorithm. This algorithm is divided into two parts: the training phase and the test phase. Table I. Algorithm. Algorithm. Input. Training. 1 Start. B Models. As seen in the Fig 2, the model is the frame of the neural network that dictates the flow of the architecture, which depends on the task to be solved. In our case it is an encoder-decoder architecture for performing semantic segmentation. 1. UNet. UNet as seen in Fig 3, is one of the most common architectures for semantic segmentation. The UNet model was developed not only as a means to identify or classify the image, also to find or localize whether the particular area of interest lies. The way it works is by classifying each pixel on the image and makes sure that the output image has the same size as the input image. The explanation for its name is pretty much evident from the architecture seen in figure. This architecture can be broken down into two parts, viz. the contraction path or simply the encoder, which essentially captures the context of the image, and the expansion path, or commonly known as the decoder, which is responsible to convert the acquired context into an output image of appropriate dimensions. The encoder can simply be thought of as a simple CNN consisting of multiple convolutions and pooling layers. The decoder on the hand does contain a convolution layer but does not contain any pooling layers, as its goal is to upsampling the image, and pooling layers are usually used to downsamples the image. For upsampling the image, instead of using some predefined method to upsample the image, we use transpose convolution, where we can learn the weights similar to convolution layer but with the intention of upsampling the image. This architecture is essentially fully convolutions network, which means that it does not contain any dense layers, thereby enabling us to use any image of any dimension. Fig 3. UNet architecture. Multi-channel feature maps are represented using blue box. The top of the box corresponds to the number of channels. The lower left edge of the box represents the XY size. Different operations are denoted by the arrows. 2. LinkNet. LinkNet as seen in Fig 4 is a lightweight, fast architecture used for semantic segmentation. This model is also an encoder-decoder architecture. They are quite similar to ladder networks, which contain lateral connection to the decoder blocks. Also, the decoder has fairly a smaller number of parameters due to channel reduction, and the decoder output is simply added with the corresponding encoder block in an element-wise fashion. The image is passed from a series a decoder, which breaks down the image into fundamental patterns which we need to extract, and the decoder builds the image back up. 3. Feature Pyramid Network, FPN, is shown in Fig 5, as seen with other models for semantic segmentation, has two paths, the bottom-up pathway and the top-down pathway. The bottom-up pathway is nothing but a feed-forward computation of the backbone CNN, whereas top-down pathway is responsible for generating the feature maps from low resolution to high resolution. In top-down pathway, each layer is upsampled by a factor of 2 and it uses a method known as nearest neighbor. But it also receives a lateral connection from corresponding layer for the bottom-up pathway on which an 1x1 convolution is applied in order to eliminate the channel's dimension, after which a simple element-wise addition is done to generate the next layer. Finally, a 3x3 convolution is applied to each feature map and then the output, and then these are upsampled according to their respective dimension. The results from all feature maps is upsampled and concatenated and then downsampled to get the final output. See backbones. As seen in the Fig 2, the backbones are the building blocks of the neural network. These are the actual layers of the network, such as convolution, pooling, upsampling, etc. 1. ResNet 18. As the size and the resolution of images keeps growing with time, there is a need for ways to train more deeper neural networks. But as we keep adding more and more layers, newer problems arise, such as vanishing gradients and degradation problem. The degradation problem basically means that the more layers we keep adding, the accuracy will start to saturate and might degrade after a certain number of layers. ResNet basically works on the idea of skip connection, as we can see in the given Fig 6. The left figure shows normal convolution layers and right figure specifies that the input is passed on to the output of the convolution layer. ResNet allows the flow of important information from the initial layers to the later layers, ensuring that the later layers performs just as good as the earlier layers on the image. ResNet 18 is used as a backbone for various models: faster RCNN, FCN and UNet. 2. Efficient net. The usual approach of choosing a neural network architecture suitable for the problem is to select some tried and tested architecture for a similar kind of problem, as done in case of transfer learning. But if there is a need for creation of custom architecture, then the approach is to vary the components of architecture, such as the number of neurons in each layer, the number of layers, etc. Efficient net, as seen in Fig. 7, proposes a sound approach in scaling the width, depth, and resolution in a systematic way, which is known as compound scaling. There are 8 variants of efficient net, ranging from efficient net 0 to efficient net 7, wherein efficient net 0 has least number of parameters and efficient net 7 has most number of parameters. For our study we have used efficient net 0 as a backbone. Fig 7. Efficient net, A, is a baseline model, B, D, are conventional scaling that only increases one dimension of model width, depth, or resolution. E, is our proposed compound scaling method that uniformly scales all 3 dimensions with a fixed ratio. V result. So, as discussed earlier, we used 3 models with 2 backbones and ran each of them for 20 epochs. We measured the metrics such as training and validation loss, IOU, F1 score, F2 score, precision, recall, as well as the trainable and non-trainable parameters for each of the models. All of these models were run on Google Colab environment. We used Atom as optimizer with a learning rate of 0.0001. Also, all these backbones were initialized with their ImageNet 11 weights to provide a fair starting point in training. The loss used for training the networks is a combination of binary cross-entropy and Jacob loss. First observation, as shown in the Table 2, is the training and validation loss. For both training and validation loss, all the ResNet variants minimized the loss more than an efficient net counterpart in 20 epochs. Second observation, as shown in the Table 1, is the training and validation loss. This being a binary segmentation problem, the IOU score achieved are quite high for both training and validation set. Again, the ResNet variants perform slightly better than their efficient net counterpart. Third observation, as shown in the Table 1, are the F1, F2, precision and recall scores. Here again the ResNet variants perform slightly better than their efficient net counterparts. Fourth observation, as shown in the Table 1, is the number of trainable parameter for each architecture. It is observed that the efficient net variants have less amount of trainable parameters than ResNet. For the UNet architecture, ResNet variant has approximately 42% more trainable parameters than EfficientNet. For the LinkNet architecture, ResNet variant has approximately 90% more trainable parameters than EfficientNet. For the EfficientNet architecture, ResNet variant has approximately 97% more trainable parameters than EfficientNet. Fifth observation, as shown in the Table 1, is the total number of parameter, trainable and non-trainable, for each architecture. For the UNet architecture, ResNet variant has approximately 41% more parameters than EfficientNet. For the LinkNet architecture, ResNet variant has approximately 88% more trainable parameters than EfficientNet. For the FPN architecture, ResNet variant has approximately 96% more trainable parameters than EfficientNet. 6. Conclusion. In this paper, we tried out various encoder-decoder approaches of semantic segmentation for our road network extraction dataset. The observations from previous sections help us in deriving the conclusions as seen in Fig. 8. First conclusion is that ResNet architecture outperforms all its EfficientNet counterparts by a small margin in the similar settings, that is, each of them is executed for 20 epochs using Atom as an optimizer with the same learning rates and using their respective ImageNet weights for transfer learning. So in terms of accuracy, ResNet is the ideal choice. Second conclusion is that ResNet architecture is highly overparameterized than EfficientNet counterparts. ResNet variants have anywhere between 42% to 98% more parameters than EfficientNet variants, which depends on the model. Thus, it can be concluded that EfficientNet outperforms ResNet by a major margin in terms of both time and space complexity, making it ideal for computation with limited amount of resources. As we have seen in our dataset, satellite images can have large dimensions not only in terms of the length and breadth, but also in terms of channels. Although our images had 3 channels, satellite images can have many more channels, making it difficult to train them on large models. So, it is ideal to use architectures such as EfficientNet, that not only give comparable results to architectures like ResNet, but also provide a better space and time complexity, at both training and inference time.